Section 7.7, Writing Quadratic Equations and Functions. In this section, we're going to take a look at a way to write equations out given pieces of information, as opposed to looking at an equation and coming up with characteristics of the graph. So we're going to look at things like the roots and the coefficients of a quadratic and think about how those are related, and then we're going to write quadratic equations or function using information about those. At the end of this, we're going to take a look at some applications of this. Now remember that a quadratic function can be written in two forms, standard form or vertex form, but we also have a third form that's frequently used, and it's really, you can think of it as factored form or intercept form or root form, where we have the roots of the equation when it's set equal to 0. So we call this root form because we're really saying that these would be the roots if this was set equal to 0. Now if we take a look at this, what we're going to notice here is that if we multiply this out, we can get some information from this equation right here. So let's multiply this out. We're going to have a times x squared. Outer is going to give me negative r2x. Inner is negative r1x. And last is positive r1, r2. Then we'll notice that the middle terms have a common variable of x. And what you'll notice here is that this became a plus sign because we factored out a negative x from here and a negative x from here, making these both positives. What I'm going to do now is I'm going to just rewrite this a little bit differently. I'm going to distribute the a to all terms. The a goes like right here. We'll have and now what we'll notice is, if we try to put this so that it looks like it's in standard form, we'll start by writing like this. And we'll think about the fact that this term at the end is just a constant. The product of a, the first root, and the second root, whatever they may be. And the next coefficient over here, we're going to see this in black, is going to be a minus a times the quantity r1 or r2, it doesn't matter what order. Remember, addition is commutative, plus r2. So this is the equation we end up getting when we simplify this as far as possible. Now what we're going to notice next is this. If we look at this equation here, we'll see that this is really the sum of the roots, r1 plus r2, and this is the product of the roots, r1 times r2. And this a value is just another coefficient in front of it. Remember that in standard form, a quadratic really reads ax squared plus bx plus c equals 0. So what this means is that this whole thing here is b. This whole thing here is c. So this negative a parentheses r1 plus r2, well, that's really just b. And this a, r1, r2, that's really just c. And what this allows me to do is allows me to solve for the sum of roots over here by just dividing by negative a. Okay, so that's negative b over a. Here, if I just divide by a, I have the product of roots. So this is pretty amazing to think about. The sum of the roots of any quadratic, the sum of the roots, will always be equal to negative b over a if you're looking at the standard form of a quadratic. The product of any roots of any quadratic will always be equal to c over a if your quadratic is then in standard form. Example 1 says find a quadratic equation with roots of quantity 3 plus I over 2 and quantity 3 minus I over 2 that has integral coefficients. So this simply means that a, b, and c have to be whole numbers. Okay, integers, whole numbers and their negatives really. So let's take a look at this one. The sum of the roots is quite simple. Common denominator means carry it over. Add the numerator. You get 6 plus 0, or just 6. I's cancel, giving you a value of 3 for the sum of roots. And that's really negative b over a. Next, the product of roots. I have to remember to do this, and then FOIL the top. When I FOIL the top, the outer and the inner terms cancel because these are binomial conjugates. So I get 9 minus 3i plus 3i, canceling, and then minus I squared all over 4. Well, 9 minus I squared is really 9 minus negative 1, or 10 over 4, which is 5 halves. So that tells me that the product of roots is 5 halves, which is really c over a. Now it's really important to notice that it's really the ratio of c to a that's 5 halves, and the ratio of negative b to a that's 3. So in this case, c could be like 10, and a could be 4. C could be 20, and a could be 8. All of these values all reduce to 5 halves though. So we don't know what the values are. But if c were 5 and a were 2, that would work. So we could start by picking those values. But it doesn't always work out easily, because then it makes b difficult to figure out what that is. Well, then you have to say, okay, well, a was 2. Since a was 2, if a is 2 here, move the 2 up and divide, that makes b negative 6. So that would work. But there's an easier way to do it. Assume that a is 1 for now. Assume that a is 1. And your function becomes the following. 1x squared. B in this case would then be, let's take a look back up here. Okay, if I assume that a is 1, makes this a 1. So I move the 1 up and divide, it makes b negative 3 in this case. And that makes c, assuming that a is 1 again. Okay, that makes c just equal to c over 1, or 5 halves right there. Well, the problem now is that these are not integer values. So we need to multiply everything by 2. And as a result, we end up getting exactly what we had supposed had we had made those values exact. So had we chosen c to be 5, and a, which was here, to be 2, there c is 5, a is 2, b ends up being negative 6, which makes sense, because when we go back up here, this becomes negative 6 over a, which is 2, so positive 6 over 2, that gives us the 3 for the sum of roots. So this is our function with integer values as coefficients. I could have done this. It could also be, and that works, because those give me the same roots. Nothing's changing here. All I'm changing is the stretchiness of the graph in a sense. Okay, whether the graph stretches up or down, so it's a vertical stretch. So this would just be a steeper graph. This graph would be steeper than this one, but it would have the same roots of the graph. Okay, the same roots. Now in this problem, it's really good to note that the roots are imaginary, so we're not going to really see these roots on the graph, but if we were to set this function equal to 0, it doesn't matter which one of these we use, we get the same roots. But this is the answer we're going to use here, okay, because this is the result we get that has the smallest integer values that we can use. Okay, example 2 says to find the roots of 2y squared plus y minus 5 equals 0, and to check the answer using the sum and product of roots theorem. So we're going to start this problem by going ahead to find the actual roots. So to do that, we could just use the quadratic formula. So x equals, or in this case y equals, opposite of b, plus or minus the square root of b squared minus 4 times a times c all over 2a. Now for a problem like this, we're going to get a result, and our result ends up being negative 1 plus or minus root 41 over 4. And we want to check that these answers are right as roots based on using the sum and product of roots theorem. So we have two roots clearly, and they're binomial conjugates. So if we find the sum of them, we could say, alright, well let's see. Negative 1 plus root 41 over 4 plus negative 1 minus root 41 over 4. And if we have a common denominator, the denominator is still 4. Adding the numerators together, when you add conjugates, the plus or minus part drops off. So you're just going to get a negative 2 there, which gives you negative 1/2. So that's the sum of the roots. So negative b over a, the sum of roots, is equal to negative 1/2. Let's see if that's true at the end. Well, we can check already, actually. Negative b over a would be negative 1, right? Because there's a 1 there, over 2, negative 1 over 2. So far we're good. Let's find the product of roots to prove this now. Product of roots is the same setup, except in between it, we don't have a plus sign. And with the product of roots, the denominator is just 16. The numerator, though, we have to remember that we're foiling, but really the inner and outer parts of the FOIL don't matter, because these are, again, binomial conjugates. So we're going to get negative 1 times negative 1, which is 1, and inner and outer are going to be root 41 and negative root 41, and then last is going to give me minus 41. Because again, remember that when you're multiplying the last part, root 41 times root 41 is just 1, but it's minus. So it's going to become negative 40 over 16. Well, let's take a look and reduce that. We can reduce them both by factors of 8, making this negative, by factors of 8, not factors of 5, making this negative 5 over 2. And that is equal to c over a. Well, let's go back up to the original and see if that reduces. Well, it's exactly right. Here's 5 over 2. Well, it's negative 5 over 2 because it's c over a. So we do prove that this is true and that our roots are correct. So again, we got the roots, and then these two things are just to verify that they're correct. Example 3 says to find a quadratic function with a minimum value, negative 3, whose graph has x-intercepts of 1 and 3. So right away we can draw this. Right? We can do this. Think about x-intercepts of 1 and 3. And we can say to ourselves that there's a minimum. If there's a minimum, it's got to open upward. Now the value of the minimum is negative 3. So we know that the value of the minimum, so the graph is going to be down here. Here's the value of the minimum right here at negative 3. Well, the question becomes, what's the actual coordinate? Well, if this is 1, 0, and this is 3, 0, and this we know that the vertex, or the minimum or the maximum, is on the axis of symmetry, it means that this axis of symmetry has to be x equals 2. So this coordinate is just 2 from the axis of symmetry, and then this negative 3 here. So we've got two intercepts and a coordinate. So let's take a look at intercept form. So we're trying to find a quadratic function. I'm using intercept form because I've got the intercepts. This becomes x minus 1 and x minus 3. Now, the question is this, though. We need to get a. We can't get a until we do something else. And we use these two coordinates. So let's use the third coordinate here. 2, negative 3. Well, 2 is x and y is negative 3. So there's the y and there's the x's. So 2 minus 1, well, that's going to be 1. 2 minus 3 is negative 1. Those are always going to be opposite of each other because of symmetry. And then we're going to have positive 3 for a. And it makes sense that a is positive because we said the graph is opening up. Okay? So the final answer is f of x equals 3, parentheses, x minus 1, x minus 3. So this is our final answer here. Example 4 says that a rectangular chicken pen is to be constructed alongside a house with 16 meters of fencing. So right away, bird's eye view, here's the house. Here's the chicken pen with 3 sides because we're using the house. The house serves as one side. Determine the greatest possible area. So we want to maximize our area. Now we know that this, we could say, is our width and our width and our length. We know that there's 60 meters of fencing available. Well, that's really talking about the perimeter of the fencing because it's meters, not meters squared, which would be area. So we know that this and this and this all together has to be 60 meters of fencing. So W plus L equals 60 meters, or 2W plus L equals 60. Well, that's good so far. That gives me a relationship between W and L. And I want to maximize the area. So let's think about this as a function. Remember, if we can write the area as a function, we can find its maximum value by finding the vertex. So the area function, well, area is just width times length, or length times width. But this is two variables in it. So there's no way I can graph this or think of this as a function right now until I make it a little bit easier. So what we can do is, we can use what's called our constraint. This is our constraint right here. And our constraint tells us that we have a limited amount of fencing. So it's like a limitation on our resources. So we can subtract the 2w to solve for L here. Why am I doing that? I'm doing that because now I can use substitution method and plug it in for L. So this is still W, and for L we're going to plug in 60 minus 2W. And now the area is a function of only one variable. So we'll say that the area is a function of the width, like f of x, this is a of w, and this is going to become 60w minus 2w squared. I'm going to write this in standard form as negative 2w squared plus 60w. The reason I wrote it in standard form is because I'm going to want to find the axis of symmetry so I can find the vertex. And the axis of symmetry is, remember, x equals, or in this case w equals, negative b over 2a. Well, negative b is really going to be negative 60 over 2 times negative 2, or negative 60 over negative 4, which is 15. So this tells me that the area will be maximized when the width is 15 meters. When the width is 15 meters, we're going to have a maximum area. Well, what's happening here really is this. We're looking at a function in the first quadrant, okay? And we're saying to ourselves that at some point along this way, this is the w-axis, this is the area axis. When the width is 15, so this would be 15, we have a maximum area over here. But the goal is to find that area. So let's take the area function and plug in 15 to find the maximum area. We have negative 2 times 15 squared plus 60 times 15. This is going to result in a value of 450. And since it's an area, it's square meters. So in reality, this coordinate, remember, this is 15, comma, 450. Okay, so again, whatever this independent variable turned out to be goes along this axis, and the value we get for the axis symmetry gets plugged in for the x-coordinate of the vertex, or plugged back into the function to give us the y value of the vertex, or the value of the maximum area. So we have currently maximized this function. Note that this had to be negative, because the graph has to open down to give us a maximum value, which is what we're looking for. Example 5 says a ball is thrown vertically upward with an initial velocity of 12 meters per second. Its height after a given time t seconds is given by h of t equals v0t minus 4.9 t squared. Determine how high the ball goes, max height, and after how many seconds this occurs, the time. So let's take a look here. We've got h of t equals. Now let's plug in our initial velocity, 12t, right? This 12 goes in here, minus 4.9 t squared. Well, graphically speaking, again, this is going to look like this, where the height is along the y-axis and the time is along the x-axis. So if we could find the time to max height, it's like we're finding the axis of symmetry. Remember, this coordinate is really time, comma, height. So if we can find the x-coordinate of the vertex, which is really the axis of symmetry, we get the time, or after how many seconds it occurs, then we can plug that back into the height function to figure out how high the ball goes. So let's put this in standard form. Noticing again that we have a negative leading coefficient. That has to happen because the graph opens down and it's negative, the a value. So let's find the time. Time equals negative b over 2a, right? It's really x equals, but x is time. So what I end up getting here is negative 12 over 2 times negative 4.9. So it's really negative 12 over negative 9.8, which turns out to be 1.2. And my units here, okay, my units of t is in seconds. So after 1.2 seconds, it reaches max height. Now the question is find the max height, so let's plug in 1.2 seconds. And what I'm going to get as a result of this, plugging in and evaluating, is 7.3 meters. So again, this occurs after 1.2 seconds and the height is 7.3 meters. So the coordinate of the vertex is really 1.2 comma 7.3. Example 6 says if the production cost function developed by workers at a video game company is represented by C of n equals 2.1 times the quantity n squared minus 3.5n plus 4.7, where n is the amount of games sold in millions and C of n is the company cost in $10,000s of dollars, then determine the amount of video games that should be produced to minimize this cost. And the question becomes, what is the cost for that game production? What is the cost for the game production afterward? So, we clearly have a positive A value, which will be distributed in a moment. It's positive because the graph has to open up to give us a minimum value. Again, we're trying to minimize the cost function. So this is the same problem as the last one and the other one before that. I'm going to write C of n equals 2.1 n squared minus 7.35 n plus 9.87. So distribute, right? Next, let's remember that this is along our axes. This is n, this is C of n. So the cost, okay, is going to be very high when you only have a few games produced. But as you get more and more games, it gets cheaper to produce them. But there's a certain amount, and once you hit it, it's the minimum cost value per game. And then that is going to go back up. So we're trying to find this minimum cost as a whole, and then we can find the cost per game. So to find a minimum, we have to find the axis symmetry. So instead of x equals negative b over 2a, n, the number of games, equals negative b over 2a. Which is clearly positive because it's negative, negative, and that's going to give me 1.75. So that's the coordinate here. Okay? Now, it says how many video games should be produced. The amount. It's not 1.75 video games. The n is in the amount of games in millions. So 1.75 millions, or 1,750,000 games. That's the first part. But now we want to figure out what is the cost for that game production. The cost function, remember, is really the y value. So let's plug in x of 1.75, not 1.75 million, but just 1.75, which is my coordinate. Plug it in here and here to give me the y value. And what we get as a result after plugging this in is 3.43. But remember, that can't be the cost, right? It doesn't make much sense. That's the cost in tens of thousands of dollars. So multiply this by $10,000 to give you the amount of $34,300 as the cost to make all of these games. Now, if you want to know what the cost per game is, take the amount of dollars over the amount of games, right? Cost per number of games. So 34,300 divided by 1.75 million games makes it really only $0.02 per game, which means it was about 2 cents every game. And obviously it's cheap to produce the games, like to actually manufacture them, but when you pay like $50, $60 for a game, you're paying for the engineering research that goes into it, for the computer coders that are writing all those games.